we're going to kick off after the 30-minute break, rather than having a 45-minute break. I'm sure you will be tired of hearing my voice at the end of the day because this is my second talk, and I will be parting in on clients a bit later as well. Anyway, I'm going to talk today about the importance of writing portable UEFI drivers, especially to me, but also I'm going to try to explain why that's important to you. Sorry, am I too full of myself? I should introduce myself. My name is Lindholm. I work for Linaro, and I work as one of the maintainers of the Core EDK2 project. I'm going to start with a quick overview of the concept of what constitutes an architecture and what constitutes a platform. Go through a bit more details about UEFI and ARM, then go through practical differences between systems you might be more familiar with than ARM systems, and then a little bit about testing on different platforms, and then like one final slide. So, architectures versus platforms. Porting drivers to other architectures is not just a question of changing the instruction set. UEFI defines fully portable interfaces, but x86 PC is a very forgiving platform that lets you get away with shortcuts that are not actually portable to other platforms, other architectures. x86, it's basically the PC platform people talk about. ARM has nothing like that. ARM is very flexible and permits very varying and different system designs that you would just not see in a PC implementation. So to give a random example here, memory organization is a good way to start. ARM architecture does not specify anything about the CPU's view of physical address space. So, that's it. Looking at a PC memory map, you know that you're always going to have some RAM that starts at address 0. And you know there's going to be a reserve bit of something at the top of the lowest 4 gigabytes, and you're probably going to have some more RAM immediately following 4 gigabytes. Note that this is not a linear scale. Top half is the first 4 gigs, and the bottom half is everything else. On ARM, I'm giving 2 example systems here. There's many different combinations you can see. It would be totally valid either to have, for example, all of the first 4 gigabytes to be RAM, and then have some MMIO beyond that, and some other stuff, and then some more RAM. Or you could have all of the first 4 gigabytes to be MMIO space, and then have something else, and then have some DRAM. So there are assumptions about memory layout that will hold true on any PC platform you ever come across, but you cannot make such assumptions about ARM even between different ARM platforms. A key note as well is that some of the technologies like ACPI and SMBIOS on PC have had hooks back from really going back to the pre-UEFI days and BIOS, where you can go searching through well-defined areas of memory to find these tables. That's not possible to do on ARM, and in fact, you should never ever in Linux have the magic devmem device node available at all, because if your entire low address space is MMIO and you go crawling through it at runtime, that's a very nice way to crash an otherwise fully functional server. So, I'm going to mostly ignore 32-bit ARM in this room because I don't think we have that many people here who would be interested in it. But support for 64-bit ARM was introduced in UEFI 2.4 in June 2013. And pretty much as soon as physically possible after that, the support was merged into EDK2 a couple of weeks after that. In UEFI, 32-bit ARM has the name ARM, and 64-bit ARM has the name ARch64, just for future reference in this presentation. I say for practical purposes, no processors older than ARM architecture V7, which was 32-bit architecture, can implement support for UEFI. But as I said, for data centers, we only really care about ARch64. ARM doesn't make silicon, right? ARM licenses processors or licenses the architecture so that other people can implement processors conforming to the ARM architecture. This lets people, lets ARM's licensees innovate a lot and do very, very different things, but that also means that they do very different things, which can lead to fragmentation. UEFI is one way that we've used to try to not necessarily get rid of, but to reduce the impact of this fragmentation. But ARM's also been working on various companion specifications to describe how to create systems that can actually be supported by UEFI. I mean, Dong has been talking about SPSA, there's also the SPBR and other one. So if you follow those specifications, you can create a system that will just work, but you need to take care of any existing presumptions that you have in code already. Linaro works completely in the open source side of things, and we help enable the ecosystem, the ARM ecosystem, to collaborate together on items that affect all ARM processor manufacturers, even though they are competitors, naturally. So here's one of my favorite phrases. Differentiation is a word that ARM likes to use about why this flexibility is important. I like to emphasize that it's sometimes some things you shouldn't be innovative about. Sometimes you're just being different, and that's not necessarily a good thing. I already said all this in the last slide, didn't I? So we have the server-based system architecture defines the hardware bits that you need to implement in specific ways in order for there to be any chance to run UEFI and to run off-the-shelf operating systems. The SPBR server-based boot requirements basically specifies things that your UEFI implementation, that your firmware implementation needs to follow in order for this to hold true. And there is work underway to do the same thing on the embedded side with an embedded-based boot requirements. Right. I'm going to talk about practical differences between PC and ARM, we could say. And I'm going to start with a bit of a tangent, which is the topic of option ROM emulation. So, one problem we have is, and it's really good that we have the FlightFest here to help out with this, is that when you have a PCI card that you want to use in your boot firmware, you need to have a driver for that. And normally that comes in your option ROM already on your card. But many vendors have not yet ported their device drivers to ARM. So to try to work around this a bit, Arch sitting in the back and Alex Graf at SUSE put together a solution that lets you actually emulate the x86 option ROMs that are already shipping on these cards. The problem with this approach, and how it turned out to be quite useful as a learning experience for us to see the kinds of things people get wrong, is that if you want to perfectly emulate the PC behavior on ARM, you also need to act correctly for all the bugs that are currently in place in the drivers and are letting them accidentally work on PC. some common issues we saw was, and this is my personal favorite, was that the failure to check for null pointers would give you a large number of accesses near physical address 0. But on a PC, you always have some RAM at address 0, so as long as whatever was there wasn't that important to you, you never noticed it. If it was important to you, you did. But on an ARM system, go back to the previous slide, you might only have MMIO down there. You've taken memory access error when you're trying to access it, so that's bad. Many platforms have had, for, I don't know, paranoia reasons, for CSM compatibility or whatever, both in the UEFI implementations, but also in the device drivers, made assumptions that, oh, we'll try to only use memory below 4 gigabytes because we can't trust anything else. That's fine if you have any RAM below 4 gigabytes, but if you don't, then that's not going to work very well on ARM. And another, the usual problem is the failure to use the proper interfaces that UEFI specifies for PCI and DMI management. None of these things would trigger an error on a PC platform, but they're all technically bugs. There is a good, you can get hold of the presentation afterwards, because that's not a good URL to remember off your hand. But there's a good presentation that Alex Graf gave about the details of the emulation at KBM Forum last year. Yeah, so I mentioned the importance of using the proper interfaces for PCI. And the reason for that is that the ARM architecture doesn't specify anything about PCI. So anything that's permitted by PCIe can be found on an ARM system. Again, on PC systems, everything tends to kind of look the same. On ARM system, that's not necessarily true. So any of these things could happen in a real ARM system. You could have different memory spaces between the CPU and the peripheral devices. So you might have to translate on outbound transactions, on inbound transactions. You might not have cache coherent DMA, which is completely legal, PCIe. In SBSA, we mandate that you must have cache coherent DMA, but you don't have to have SBSA in order to have UEFI on ARM. So if you have a non-server class platform on ARM, it might not have cache coherent DMA. You can have a single outbound MMIO window, so you can only have one. You can have no outbound I/O window whatsoever. So I/O accesses, as opposed to MMIO accesses, are generally not a popular thing on ARM. And you can have multiple eCam config windows located anywhere in the address space. So it's important to follow the rules if you do want to get these working on ARM. And here's a good diagram that Art drew. This is basically what any PC system looks like. You have your SoC, you have a host bridge with a bunch of root ports and PCI devices on the other side of that, and this probably looks very familiar to all of you. But key thing to keep in mind here is that all memory transactions happen in the same address space. Now this is a sort of worst case situation, but we also actually have real systems that look like this. That's completely legal, and you might come across on an ARM platform. You might have multiple different host bridges, each with maybe only one root port, maybe without a root port at all. You may need translations going both directions, and especially if you're doing peer-to-peer accesses, then things get really complicated. So, but again, if you're using the correct interfaces to handle this in UEFI, it will deal with this for you. You don't need to worry about it manually. If you're used to just passing pointers to buffers around directly without using the interfaces, things can get interesting. So, map and unmap methods are really important to actually use. Allocate buffer deals with the non-cache coherent DMA as well, so you don't need to manually clean your caches or anything like that. Get bar attributes looks at the translation offsets, but as I said, many drivers cut corners and technically violate the UEFI spec by doing the thing that still gets to work in code on PC, and where they don't cause any unexpected behavior. But on any more interesting, in the comical use of the word interesting, PCA topologies, that's just not going to work. That's not an ARM-specific thing, it's just anything that doesn't look just like PC. So we have a good example here from actually taken from EDK2, where a conscientious programmer has properly called allocate buffer and then maps the buffer and then uses that mapped address for the transaction. And then we have, because we use the allocate buffer, we can then use the map call, and mapped address can the mapped address can deviate from both the virtual and physical addresses as seen by the CPU. And the size of the mapping can deviate from what you requested. That depends on the underlying mechanisms of the hardware. On a PC, you could get away with doing just this, because you're always going to have the same addresses visible to the CPU and to the PCI device. And it's always going to be coherent. So you could just allocate some memory and then use that, and it'll all just work. I went through most of this in the beginning of the presentation, but the key thing is that if you have PCI devices that only support 32-bit DMA, then you have a real problem if your UEFI implementation only lets you use 4 gigabytes. I don't think that's a problem on any ARM system out there anymore, but we did have that initially. What we do find is that many UEFI drivers, PCI drivers, don't set the dual address cycle attribute, which you need in order to be able to use more than 32-bit DMA. So even if you've done everything else right, you still need to configure the device to actually use 64-bit accesses. And yeah, much existing code actually goes and explicitly checks, oh, is this address beyond 4 gigabytes? Oh, then I can't use it. Which is a problem, again, if you only have RAM above 4 gigabytes. And yeah, there's some workarounds you can do with an IOMMU if the physical hardware doesn't actually support 64-bit DMA, but preferably just try to avoid that. You should assume that ARM platforms will use at least 40 bits of address space for DMA. And a final note that doesn't really fit in on this slide is that going back to the PC memory map address map I showed before, there is never RAM at the top of the 4 gigabyte address space on the PC, because that's bias vectors and things. I've found a few examples of code doing 32-bit arithmetic and getting it wrong when you pass in a buffer that happens to have been allocated near the top of the 4 gigabyte range. So try not to use 32-bit arithmetic if using 64-bit addressing. Again, same as mentioned before, for DMA, you may have non-cache coherent DMA on ARM systems, but as long as you use the allocate buffer and map and unmap, cache maintenance will happen magically and you don't need to worry about it. Another interesting bit, which I should add does not apply to PCI, so maybe most of you won't care. So this applies to platform drivers. So UEFI is really a single-threaded execution environment. If you're doing any clever stuff under the hood, like using the PI-MP protocol, then you have explicit synchronization mechanisms that you can use to manage that. So that's not a problem as such. But it's worth keeping in mind that ARM does not guarantee the ordering of memory accesses, even in regions marked as devices strongly ordered, unless they fall within the same 1 kilobyte size, 1 kilobyte region. So if you're doing something where you need to order 2 memory accesses specifically in time, then you need to use the memory fence macro to insert a barrier for the access. Typical examples of this is if you write a DMA descriptor and then write to a peripheral to initiate a transaction, or if you write to a register and then need code for a change to happen, then you need to make sure that that write has actually gone out before you can go and read it back again. So, yeah, so not important for PCI, but if you write platform drivers for ARM, it's important to keep in mind. So Art was quite happy when he discovered that actually this is going to come and bite people anyway if they start working with encrypted memory. So even if you don't think you're going to work on ARM, if you think you're going to be working on systems that have encrypted memory, the same mechanisms that will make your drivers work on ARM will also make them work with encrypted memory. So as long as you use the proper allocate, map, and unmap actions, then the interfaces will make sure that you get the correct, the decrypted version of the memory rather than some random thing and that's been garbled rather than decrypted. ARD has helpfully put together a worst-case system, which we've nicknamed Chucky, for triggering the most common issues in all drivers. So in the Linaro test suite, we have a system with no RAM accessible below 4 gigabytes, no 32-bit DMA, no RAM, well, so you can't use 32-bit DMA, and there's no RAM near 0 to hide null pointer B references. And there's non-one-to-one mapping between PCI and CPU. So anyone who has an AR64 driver is welcome to visit the Linaro test suite and try it out. Even if you don't have anything scheduled, I'm running by the plan that if the door to the Linaro test suite is open, you're welcome to come in, and if we're busy, then you can come back later time. Art.
It also has non-cache coherent DMA.
Caching coherent DMA.
Yeah.
Yeah, sorry. The system also has caching coherent DMA. And of course, if you don't have an AR64 driver, you're still more than welcome to visit us, and we can talk to you and see how we can help you create one. And if you do want to do that, it's useful to know that even if you're using Visual Studio for your development today, as long as it's at least Visual Studio 2017 version 15.4, there is AR64 support in Visual Studio these days. But you also have Clang and GCC support for building ARM drivers. I think, yeah, so, okay, to summarize everything. It's completely possible to write and drive an application that can be easily compiled for either x64 or AR64 architectures, and will work on both of them, and it will actually be more correct than a driver that won't. It's also very much possible to write a driver that only works on x64 and not AR64, but technically that's probably usually down to bugs. Writing drivers portably increases code correctness and reliability. And if you test it on multiple architectures, that's even better. That's all for me. Any questions? Okay. Thank you very much.